This video for section 13.9, I will be going over optimization problem for a function of two variables using the second partials test. In this question, we want to find the minimum distance from the point 1, 2, 3 to the plane 2x plus 3y plus z equals 12. Now, again, we have this point out in space and we have a plane here. We want to find the minimum distance from a point on the plane to this point here in space, 1, 2, 3. We need to come up with an equation that we're going to try to maximize or minimize. In this case, we want to minimize the distance. So let's go ahead and find an equation for the distance between a point on the plane. Say this point on the plane has coordinates x, y, z, and this point in space here has coordinates 1, 2, 3. So we want to use the distance formula for the distance between 2 points in space. The distance formula is equal to the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared plus z sub 2 minus z sub 1 squared. So that's our distance equation. This is what we're trying to maximize. But we're going to be plugging in the points, a point on the plane and the point in space. When we plug in the point on the plane, we get the equation for the distance is, let's say, x minus 1 quantity squared plus y minus 2 quantity squared plus z minus 3 quantity squared. Now this d function is a function of 3 variables. In order to use the second partials test, we need to find d as a function of 2 variables. Now the way we're going to take care of that is to use this equation of the plane. This is what we call our secondary equation. If we solve this equation for z, z would equal 12 minus 2x minus 3y. So we can replace the z in the distance equation with what the z equals in our secondary equation. When we do that, we get d equals the square root of the quantity x minus 1 squared plus the quantity y minus 2 squared plus the quantity, we're going to replace z with all of this, and then when we subtract 3 from that, this entire quantity minus 3, we have the 12 minus 3, that would be 9, minus 2x minus 3y, that entire quantity squared. So now we have the equation for distance, which is a function of 2 variables, and we can apply the second partials test. However, before we get started with that, I do want to mention here a shortcut here. This equation, when we're going to take the partial derivatives, can be quite tricky because of that square root. So what we're going to do is we want to minimize that distance, minimize d, but in order to give us a break here, do a shortcut, we are going to minimize d squared. Because if you can find the minimum d squared, then inherently you can find the minimum d. And if we find d squared, an equation for d squared, when you square the square root, we get the equation x minus 1 quantity squared plus y minus 2 quantity squared plus the 9 minus 2x minus 3y quantity squared. So it is going to save us some time by minimizing d squared and then going back to find the answer for the minimum d. So now we have d, which is a function of 2 variables, and we want to use the second partials test. We're going to have to take the partial derivative of this d function with respect to x, or actually, we want to take the partial derivative of this d function, a d squared function with respect to x, and then we want to take the partial derivative of this d squared function with respect to y. You can go ahead and try this one on your own, pause the video, and then come back. When you're finished, we're going to set those equal to 0 to find our critical points. When you find the partial derivative of this d squared function with respect to x, you can use the chain rule here. When you use the chain rule, you get 2 times the quantity x minus 1 plus, again, you're treating x as a variable here, treating y as a constant. So when you take the derivative of the y minus 2 quantity squared, that's a constant, so that derivative is 0. And then we're going to take the derivative of this last term using the chain rule, which would be 2 times 9 minus 2x minus 3y. And then we have to multiply by the derivative of what's inside with respect to x, and that is our negative 2. We want to then take the partial derivative of this d squared function with respect to y. When you take the derivative of this with respect to y, we treat x as a constant, and that derivative is 0. The derivative here, this of the quantity y minus 2 squared, is going to be 2 times the y minus 1 to the first power times the derivative of what's inside, plus, I'm sorry, that should be 2 minus y minus 2. And then we take the derivative of this last term squared. It's going to be 2 times 9 minus 2x minus 3y times the derivative of what's inside with respect to y, and that derivative is negative 3. Now we want to find out where these are both equal to 0 at the same time to find our critical points. Alright, to find the critical points, I'm going to go ahead and simplify this equation and simplify this equation so we can get a system of two equations with two variables. By distributing the 2 here, by distributing the 2 here, and then go ahead and distribute the negative 2, and doing the same thing here and combining like terms, we can end up with equivalent equations for those partial derivatives. Okay, so when we simplify those partial derivatives of d squared with respect to x, and distribute and combine like terms, we end up with 10x plus 12y minus 38. We're going to set that equal to 0. And then we're going to simplify that partial derivative of d squared with respect to y. And when you do that, you get 12x plus 20y minus 58 equals 0. Now you can use the graphing calculator, setting this up as a matrix to find the critical point, or you can solve the system by substitution, elimination, or the matrix method. If you use the matrix method, you want to write your equations in this form: 10x plus 12y equals 38, and then you want to do 12x plus 20y equals 58. You would create a matrix using just the coefficients of x and y and what those are equal to. When you set up the matrix, it would be, you want to reduce row echelon form of the matrix 10, 12, 12, and 20, and 38 and 58. So again, using those numbers, create a matrix in your graphing calculator with these rows and columns, and then find the command to reduce row echelon form of that matrix to find the solution. When you do that, you get a matrix that's in the form of 1, 0, 8 over 7, and 0, 1, 31 over 4. I'll go ahead and show you how I found that on my graphing calculator, so you can follow along and practice with your calculator as well. Okay, to build that matrix, you're going to turn your calculator on and go to the matrix menu. We're going to use the edit by moving the arrow to the right. We're going to edit matrix A, choosing number 1. This matrix is a 2 by 3 matrix. You can enter those numbers. And then I'm going to plug in the values for our matrix, 10, 12, oops, sorry, making sure you press enter after each number. So I entered 10, 12, and 38 into the first row, and now I'm going to enter 12, 20, and 58 into the second row of matrix A. Now once you're done entering those numbers, I press second and quit to get out of that edit mode in the matrix. Go back to the matrix menu, and in this time we're going to go to the math menu, that one in the middle, and we're going to scroll down until we find the command for RREF. That's going to reduce that matrix. And so we have the RREF command. We go back again to the matrix menu and choose the name of the matrix that we want to reduce, and we've edited A, so that's the one that we want to choose. We're going to reduce that, and notice that we get decimals here. We can convert these to fractions by pressing the math button, pressing math, and then choosing the first option for frac. It'll take the last answer displayed on your screen and write them as fractions, convert them to fractions. So that's how I get the 8 over 7 and the 31 over 4 for the solution to the system of equations. So x is equal to 8 over 7 and y is equal to 31 over 4. So that's our critical point for this function of two variables. That's the critical point for d squared. All right, so our critical point is x equals 8/3, so it's, 8 over 7, and y is equal to 31 over 4. Now, to determine if this gives you a minimum distance or a maximum distance, we want to use the second partials test. So we are going to take those higher order partial derivatives, take the derivative of d squared with respect to x and x again. So going back to this result, take the derivative of this with respect to x and you get 10. You're going to take the partial derivative with respect to y and y again of that d squared, and that will give you 20. And then you also want to find that mixed partial dxy. So if you take the derivative of the first, the partial with respect to x, now with respect to y, you get 12. So our d is found. Now this is the d in the second partials test. I'm sorry, not to be confused with the d for the distance that we're using here. The d is found by multiplying 10 times 20 minus 12 squared, and that is going to be greater than 0. It's 200 minus 144, so that is definitely greater than 0. D is greater than 0, and the partial derivative with respect to x and x again is also greater than 0. So that means we do have a relative minimum by using the second partials test. Looking at the sign of this and also looking at the sign of this, we can determine that this point does give you a minimum distance squared. Now we want to take this value here and plug it back into the original distance equation to find out what that distance is. Okay, so now, since this is our critical point that yielded a relative minimum, this is going to give us our minimum distance. So we're going to put these values in for x and y to find our distance. So 8 over 7 minus 1 squared plus y is 31 over 4 minus 2 quantity squared plus 9 minus 2 times 8 over 7 minus 3 times 31 over 4, all of that squared. If you're doing this on your calculator, which I highly recommend doing this part on your calculator, is to do everything without the square root first and simplify, and then take the square root of the result. If you do everything that's underneath the square root, you're going to get 1 over 14. So that distance is going to be the square root of 1 over 14. So that is the minimum distance from our original point, 1, 2, 3, to a point that's on the plane here. That's going to be our minimum distance, is 1 over the square root of 14.